A black object heated to a high temperature will emit a bright glow called blackbody radiation. If the intensity of each emitted frequency is plotted, you'll see a graph like this, but scientists studying this effect in the 1890s expected the graph to look like this. This discrepancy, known as the ultraviolet catastrophe, was not explained until the year 1900. That year, Max Planck proposed a theory called Planck's relation. It states that energy is emitted by atoms in packets called quanta. The minimum energy of each quantum is proportional to the emitted frequency. The actual energy of each quantum is a multiple of that. You can visualize this by imagining a box on stairs. As it moves up and down, its potential energy changes in discrete steps. Planck used his relation to determine that at high frequencies, it's more likely for a particle to emit multiple low energy quanta instead of one high energy quanta. This explains why at high frequencies, the intensity of the emitted radiation decreases. In 1905, Albert Einstein built on Planck's work to explain the photoelectric effect. The effect occurs when light hits metal, causing electrons to be released and creating a current. Surprisingly, no current is produced until the incident light has a certain threshold frequency. Einstein proposed that light was carried by photons. Each photon has a discrete amount of energy modeled using Planck's equation. The conservation of energy says that the photon's energy is equal to the sum of the energy required to release an electron and the kinetic energy of that electron. There's a minimum frequency required to release an electron, just like how a box must first be carried high enough to be placed on a shelf. The efforts of Planck and Einstein won them Nobel Prizes and ushered in a new era known as modern physics. Their work provided the foundation for understanding the quantum nature of our universe.